Okay.
So here we go. I have it now. Okay, so the outline for the talk will be to first talk about challenges for digital computing, opportunities for superconducting computing, another quantum information science proposal, which is readout, our approach, which are gates exploiting bit momentum, and then I'll talk about how we do that. I'll talk about design and testing of discrete long Josephson junctions. We'll talk about how we combine LJJs into pairs and a ballistic flip-flop gate that we'll eventually design. But then first I'll talk about a two-polarity detector that we need and some test results from that. And finally, design and simulation work where the design is eventually ended up in a physical design. So, of course, we know that CMOS computing is rapidly increasing in size and usage. Here are some information from late in 2024, and the exascale barrier was reached. That's 10 to the 21 operations per floating point operations per second. I think that's right. And the energy is about 20 megawatts for that, and that's equal to the usage of several thousand homes. And then here's a list also compiled from December of 2024, and you can see the top computing supercomputers sometimes have a energy usage of 30 megawatts. And the motivation for doing some fundamental research is, besides supercomputers, that data centers, AI, and cloud services all use a lot of power. I know this scientist, Mike Frank. He started working for Vera Computing, a new computing company, and they plan to do adiabatic reversible computing. And what they noticed in this publication is that the energy cost for switching logic decreases over time, and it's sort of leveling off as you get to these more sophisticated nodes, the latest nodes, 2 nanometers and so forth. And they believe they can achieve gains of more than 100 times in switching operation speed per unit area using a new sort of architecture for standard CMOS. And so, I don't know too much about the computing company or all those claims, but I think it's a nice introduction to our talk, which really is on superconducting computing. And I grabbed this chart from a reference that you can see down here. There's sort of fundamentally different switching in superconducting electronics than CMOS. CMOS, here's an energy consumption place where it consumes energy. It's very efficient, but still superconducting electronics consumes less energy. Of course, you have to cool down the circuits to achieve that. And also, the superconducting electronics can switch faster. It can operate with a shorter cycle time, shorter period for the clock. And I'm going to include superconducting electronic comparisons halfway through the talk, so I'm not going to talk about these different superconducting electronic types on this slide, just giving a layout of it. What I'm really going to focus on in this talk is logic that we're studying that is reversible and is ballistic. Here's CMOS in energy consumption per gate operation in, it's a little less than a femtojoule, typically, maybe almost an order of magnitude more efficient than that. And superconducting electronics can end up being on the order of a zeptojoule. And there's adiabatic types that are adiabatically powered and related to the adiabatic CMOS in some sense, but I'm not going to focus on that. I'm going to focus on this new type, which is ballistic and uses momentum of SFQ. When we compute what we have designed in the last gate that I'll show you, we have an energy consumption that has a very short delay too, such that the energy is 100 Planck's constant divided by the time of the operation. And that's not too far away from a fundamental limit. It's about a factor of 100 away from this quantum limit, which nobody believes you can go past in computing. There's Landauer here. This is the limit for reversing information. And that relates to this next slide. Oh, actually, 2 slides from now, too. There's digital logic types, and then there's reversible devices. And most logic in SFQ or in CMOS is irreversible by design. The energy cost is a charging energy in CMOS primarily, whereas in SFQ, there's energy to activate an SFQ from one cell to the other. And that's approximately an energy cost of IC phi naught. And it can be generally as much less than in CMOS. In an overlap between, let's say, reversible devices and digital devices is this area here called reversible digital. It can result in a lower gate energy from the new design. And I mentioned already there's adiabatic architectures. NSQUIDs from University of Brookhaven is one type. There's also a reversible version of something called adiabatic quantum flux parametron. That's been tested and found to have very low energy consumption, less than regular SFQ activation energies. But yes, we're going to study a ballistic logic type, and the goal is to understand ballistic free dynamics in this study to realize a logic gate, or at least the design that I'm going to tell you about. And quantum computing, you could say, well, that's a reversible device, but it's very different. And I was told there would be students here and of course, students are interested in quantum information science. And so I should mention the difference here. Quantum processors use these quantum bits that are general bits relative to classical bits. They store quantum information. Specifically, they're intended to run special algorithms named quantum algorithms. One such algorithm is called Shor's. And since quantum gates require very, very precise control on these bits, they're not pursued at all for classical algorithms. So it's a different type of special purpose computing relative to digital, which this talk is really about digital. But I'm going to mention one quantum information science proposal just to say that they're sometimes connected. There's sometimes some overlap, at least in proposals. There's the standard readout for a qubit, which has a qubit in a microwave cavity, and the microwave cavity will change frequency in response to the state of the qubit. But there was this other proposal that started back in 2006 and ended up being an experiment in 2013. And a fluxon, if it passes by a qubit, will experience a different potential barrier depending on the state of the qubit. In the case of the experiment, they grew a tri-layer long Josephson junction in an annulus like this, and they powered the fluxon to go around the ring, this annulus, in the long Josephson junction. And the qubit was prepared in different states, and they saw a different emissions frequency depending on the state of the qubit because there was a different time delay for the 2 different states. So that was a spectroscopic measurement. And we recently released something on the archive, just a theoretical quick proposal on how you might read out a qubit in single shot. It's on the archive and it was accepted into Physical Review Applied. And the idea is to use a long Josephson junction on both the left and right side of a qubit and to use a fluxonium qubit. And if we do this very briefly, we can set it up so that if we prepare the qubit in the ground state, a fluxon can come in and spend some time at the interface that at x is equal 0 is right by the qubit. and it will transmit in the ground state of the qubit. And if the qubit is in the excited state, the fluxon will reflect off. And this is just theory, but the nice thing is this little study shows that the readout time could be sub-nanosecond, and you can compare that to hundreds of nanoseconds for a standard cavity-based readout. And the qubit's only slightly perturbed, meaning which relates to something called back action, which is really small, 10 to the negative 3 or smaller. Okay, so that's just sort of a side thing to say, that's sort of interesting. But this talk really is about reversible computing and digital computing. There's an erasure cost, energy cost. Ralph Landauer realized this. If you lose a bit of information, you're going to have to dissipate log 2 KT. All our experiments are, even though they're reversible, we're at higher energy dissipations than this, partially because of the materials that we use. So in the future, they could lower relative to what we have, and we could even cross this for a demonstration potentially, or someone could. Charlie Bennett realized a mathematical model of a reversible computer, and he had this way of doing a computation in theory with a tape, and then recording the result and uncomputing or decomputing and recovering the history tape and erase and basically that in principle you've proved a reversible computer could be made, and there's no hindrance to it except perhaps, of course, the hardware. And I want to mention something about Feynman here. He was actually interested in computing during some of his career. And for an experiment at SLAC, he described a proton which has these particles, the quarks and antiquarks and gluons in the proton as partons. And I only mention this because I'm going to mention something about relativity later, and I want to give the audience some sense of what relativity is if they're electrical engineers and they didn't take a relativity course. So in this experiment, an electron is accelerated to high energy at SLAC, and it causes a scattering of the proton, and it only interacts with one constituent of the proton at a time, let's say one quark. The result is a new mass that comes out because you have energy that was put in to that nucleus from the relativistic particle, and the new mass ends up being larger than the rest mass. This is generally small for the proton, and the interesting thing about the experiment is all the new mass is just dependent on the momentum of that proton and something that can be calculated, the momentum of the photon that comes in. Anyways, so that's just sort of a flavor of some sort of relativity, but we won't really want to do anything very relativistic in some sense for a few reasons. We're going to use fluxons for our pseudoparticles, and we're not going to want to create anything new. We're not going to want new particles to come out or other things. We want everything to be very controlled. And I'll describe more about the relativity. We're really not going to be working at regular relativistic velocities, but just velocities of fluxons on the chip. But we're going to exploit the bit momentum. We're not going to power the fluxon within the gate. We're just going to use the momentum of the bit. And I want to mention some contrasting models for typical SFQ. You have DC power coming in, you have clock pulses, there's heat generated, there's generally less output bits than input bits. And the heat is pretty much exactly the activation energy for that SFQ. You can also make an irreversible model that is sort of looks simple here, where we have just the bottom of wells defined, and you have an input state A coming in, input state B coming in, and you could make up a model for an OR gate this way and say, well, we're going to merge the states or the balls that represent the one states for the A state and the B state, and the result will be, of course, a ball if either a ball came in on A or B, and there's going to be some energy lost for also the case that a ball came in on A and B. So this is just a simple activation model, and it's going to contrast what we're going to do later with reversible. Okay, so anyone that studies superconductivity knows that there's a supercurrent, which is equal to some constant of a Josephson junction times the sine of the angle of the phase difference between the two superconductors that are connected by a tunneling barrier or some other barrier. In this case, in superconducting electronics, typically it's niobium for the base electrode and the counter electrode, and aluminum oxide for the barrier. And there's something called a Josephson transmission line, which is a standard structure for transmitting SFQ forward. You have an SFQ that's primarily in one cell because there's an inductor that's large compared to these Josephson junctions that are biased. The biasing of the junctions is at about 3/4 of the critical current. And as the SFQ moves from cell to cell, there's a voltage pulse that occurs from the change of phase across the junction. And I've already mentioned the activation energy, and that is basically the energy expended by the power source and dissipated on chip for moving the SFQ one cell forward. So most students understand that, and also if you've studied superconducting electronics, you understand that there's this sinusoidal potential energy of representing a Josephson junction. There's a plasma frequency that is present if you have an unbiased junction. It turns out that the state of the system will oscillate back and forth if it's not damped, and that frequency will be related to the Josephson inductance and the capacitance, where the capacitance is something like a mass in the Josephson junction. And there's a known mechanical model for the progression of the state of the junction in phase in sort of the potential landscape of that potential surface, and it's related to the damping and also the capacitance or the mass of the particle. Now I'm going to mention one other irreversible gate. I mentioned the JTL. This toggle flip-flop is something that we're using in our experiments to measure the reversible phenomena. So, and to simulate it. So I want to mention this. If you have this circuit here called a toggle flip-flop, and the bias current comes in here, a single input pulse will be split into two paths, some of it coming down L1, some of it coming down L3. And the pulse will basically cause J1 to switch and J3 to switch initially, and that'll store an SFQ in this inductor, which is also related to this SFQ stored mostly in this inductor. And then upon a second pulse coming in, another SFQ pulse, J0 and J2 will switch, and that'll reset the toggle flip-flop back to the initial configuration with no SFQ stored, and this SFQ will exit through here. And when that SFQ exits, it basically creates a pulse out, and that took two input pulses. So there's sort of a division in frequency of 2 to 1 for the frequency ratio if you operate this over and over again. Okay, for ballistic computing, there's this classic billiard ball model that came out in the 80s, and you can, in principle, in an ideal world, make a ballistic computer out of these ideal gates. State A is represented by a ball coming in. State B is represented by a ball coming in. The two collide. If they're both there, you get an output on this port here called the AND output. If you have only A in, you'll get an output here. This is A but not B output. And if you had any B, regardless of whether it came by through itself or it was the result of collisions, you'll get an output here for an input here. And of course, this is just a model thought of in a mechanical way, just to sort of argue whether you can have ballistic gates. And the answer is yes, and in some ideal world you could. And I'm going to tell you how we have designed ballistic gates. They're different, but I want to introduce something about relativity. Again, for students that aren't used to relativity, or a lot of people, including me, didn't look at it for many years, let's say, and you kind of forget about it. So the energy of a relativistic particle is mc squared times this factor gamma, and gamma is the ratio, of course, of the total energy over the rest energy, mc squared, and it has a limit of c, the speed of light, for a small particle. And as the velocity gets larger and larger, it approaches c, the energy will eventually approach infinity in this algebraic way. Now we're going to use fluxons as pseudoparticles, and so we're not limited by some of the problems here. These had to be synchronized, and we're not going to require synchronous bits, which will be nice. Our general type of gate that we have is represented, let's say, just by this block. It has some internal state, just like SFQ electronics normally has some internal state. And for 2 inputs and 2 outputs, it would look like this. And I put different subscripts for the gamma because the energy out on one of these scatterings could be a little bit less than what's coming in. And that'll be our gate dissipation. We don't necessarily have clocks per se, or clocks can be thought of as some of the input states. And in our simulation and experiments, we design usually for gamma is equal to 1.25. And that means that the velocity relative to the limiting velocity is 0.6. And that limiting velocity is called the Swihart velocity in long Josephson junctions. It's lower than the speed of light, quite a bit lower. Okay, designing, first this is Dr. Han Kai tested some discrete long Josephson junctions in the lab, and that's very nice. Oh, and I want to introduce, what are the time constants related in a transmission line that's superconducting on our circuits. We use 2 micron line width, and there's not a big kinetic inductance effect. So our effective permeability is, roughly 1. But there's some dielectric here, and there's some effective dielectric constant using the silicon oxide dielectric and also some vacuum. That's going to be, a factor that's larger than 1, but not much larger than 1, maybe a couple. So this waves will travel down a transmission line in superconducting circuits pretty close to the speed of light, and vacuum a little bit less. But we're going to study long Josephson junctions, and we're not going to actually use this trilayer, but it helps to talk about a fluxon in a trilayer in more detail. The main energy in a fluxon in a trilayer is stored within a central 2 lambda j, and the flux in that is 1 flux quantum. Exactly, if you have thick electrodes such that there's really a path for 0, let me just say for thick electrodes. And for us, for our critical current density that we mostly use, that size is something like 40 microns. Now this trilayer, the waves in it are described by a Sine-Gordon equation, and this phi sub tt is a double derivative with respect to time. Phi sub xx is a double derivative with respect to position. This is the Swihart velocity. This is the Josephson plasma frequency that I mentioned before. And this is sine of phase, but it's a function of position now. It's not just phase at one point. And in addition to having a full fluxon in here, you can have small wave oscillations that are called plasma waves. Okay, so in a standard long Josephson junction, you basically have, I've already shown you that, and the soliton solution is known. It has the following shape given by this equation. And we're going to use a fluxon for one of the bit states and the anti-fluxon for the opposite bit state. And it's new in SFQ electronics to have used two polarities. So that's something that we encountered that. And we're going to actually fabricate it in a discrete way because it's very convenient to understand the parameters. And we've studied separately, what came out of the foundry. Did we really get the inductance that we expected? And confirmed that and gave values for that. But anyways, so the inductance per cell is small compared to the Josephson inductance of one of these JJs. And in our talk, the sort of core of that fluxon, which is 2 lambda j, is approximately 5 unit cells. Okay, so we have two measurement setups in the lab. One is a probe and a dewar. The chip nest looks like that. You put a chip right there, and then you turn this probe upside down and put it inside a dewar. And then we also have this cryo-free refrigerator. It has a probe station, which stores a chip that you study. And turns out that this one is a little bit more secure to noise, we believe, because partially it's sealed up very well, and there's lots of nested cans, and we can't have radiation coming down the throat of it so much. So because everything's pretty tightly sealed up with metal to metal surfaces. And the quick answer of what we found in this first study I want to mention is just to show that a fluxon can transmit. And how does it look when it transmits? This is our long Josephson junction. We had a SFQ, a DC to SFQ converter here, and a SFQ to DC converter with only a 20 microamp JJ for the first JJ in this detector. And we were able to launch, this is Han Kai's work here. She was able to launch and detect fluxons that had very low energy, and she was able to look at the timing distribution of the fluxon with in the dewar system versus the cryo-free refrigerator system. And the distribution's a lot tighter for the cryo-free refrigerator system, indicating that I think we believe it's lower noise on that first junction to the SFQ to DC converter. But anyways, according to calculations, we are transmitting ballistically and we're detecting, and we are very happy with this result. Okay, now to really make up gates, we combine LJJs in pairs. This is a schematic for two LJJs, and they're connected at an interface made of 3 Josephson junctions that have a shunt capacitor added to them. Okay, and we added those shunt capacitors because we're like, we want more general dynamics than the dynamics we'd get with just the intrinsic capacitance. So you can think of these long Josephson junctions as being connected. There's these terminations at the end of the JJs, but there's also this JJ here that can allow large phase winding for new operations. One of the gates that we've sort of discovered numerically, and this is Dr. Wussman, who's the main theorist in most of these papers, in the theory papers, that is, what we were able to discover is different types of gates and resonances that you would get, but some of them are just pedagogical, or fundamental and not necessarily useful. And the ID gate isn't very useful, and actually we don't think we could realize it in the lab very easily. A fluxon comes in at a later time, let's say a midpoint in time, we get something very different, and then at the end, a fluxon comes out with roughly the same momentum. But in the mid-time, what you have is actually opposite current circulation, which is kind of interesting. And but what's more useful to talk about is this NOT gate. It's fundamental, and it actually could operate in the lab. So fluxon is, this is, fluxon's coming in, and what comes out is an anti-fluxon. And there's this strange current distribution at the midpoint in time. But what happens we see in our simulation result is a fluxon is coming in here. It's wrapping the phase difference in the LJJ from 0 towards 2 pi. As the fluxon has passed it, there's a 2 pi winding, and it's traveling ballistically. There's no power, and there's no power in the gate. But when the fluxon comes in, it collides with the interface. There's some excitation on the right-hand side. You could call that a semifluxon if you want. There's some excitation on the left-hand side that you see next, and that winding is actually going above 2 pi. But then what's coming out finally is a winding from 0 to negative 2 pi. There's been a big phase slip in this across the middle of this over time. And that's related to that phi b junction phase that has accumulated a phase over time. And the nice thing about this is the gate efficiency is over 97% in optimized simulations. And so that means that of this total fluxon energy, you've lost 3% of that energy to something else besides fluxon energy, and it's plasma waves eventually in the LJJs. Okay, so I decided to include these slides, but not to cover them in detail. There's a way to understand this and model it. If you're a mechanical engineer or something, or a physicist, you might be like, well, what's really happening to make that resonance? And we have a way of describing exactly the dynamics that I just mentioned, but instead of simulating all 40 JJs, you just consider an excitation on the left-hand side and an excitation on the right-hand side that can be there or can actually disappear. And the excitation can describe a fluxon-like excitation or anti-fluxon-like excitation. It takes a fair amount of work to do all of this, but what Dr. Westman was able to confirm is that the simulation in some space that relates to our trial ansatz waveform, that exact simulation result gives us the same result if we reduce to 2 effective coordinates, one possible excitation in each LJJ. So the physics can be understood, and it relates partially to extra capacitance of the interface, which increases the mass of the fluxon as it comes towards the interface, and there's interactions between the two LJJs too. There's no damping in those in the interface, and it doesn't seem necessary as long as you just run it at some regular rep rate of, let's say, megahertz. Ballistic flip-flop is basically a little bit like the NOT gate, except we have an added storage loop at the interface. So there's the junction that can allow a phase slip of 4 pi, depending on what the dynamics give in the sort of setup gates, tuned up gates for a fluxon coming in over a range of velocities. This fluxon can come in this ballistic flip-flop and realize a shift register operation. The input bit replaces the stored bit over here. This is the time after, and what was stored before comes out using the momentum of the input fluxon. And so this is sort of a physically interesting phenomena that you don't have to power a gate. You just have to set up the dynamics carefully using the right parameters for your gate. And it also works to get this operation here with opposite bit states. What you find is you realize the NOT gate dynamics in some sense, because what has changed is the phase is changed by 4 pi in that central junction. In the case that they have the same polarity, the fluxon comes in, it slows because there's a potential barrier created by that same polarity fluxon that's stored, and then it goes forward with the original velocity approximately. There can be a little bit of energy loss, and there is whenever we run the simulation, and that's fine. I mean, but it's always small compared to the input fluxon. So we see it as sort of a ballistic reversible test case. And by doing it with the storage loop and the input bit, notice that it became asynchronous. We don't require the bits to come in at the same time, and we can generalize this gate and attach actually more pairs of long Josephson junctions to the storage loop and still realize gates. And then in contrast to flip-flops, we don't have power to switch. Of course, we're switching to whatever, in some sense, whatever comes in. But it could be used, that state could be used and distributed to other outputs. Okay. All right, this is a table for superconducting digital comparisons. I think it's very useful for students and people like myself who wants to understand how to compare different logic types. I put ours called reversible fluxon logic at the end. I sort of time ordered this. RSFQ is one of the earliest types of logic gates that stuck around. It's DC powered. AQFP and RQL are both AC powered. There's something called XSFQ, which has 2 rails for the 2 bit states. The bit state has a fluxon on one rail, or the other rail for the 1 and 0 states. And ours uses an LJJ for the bit state. It's either a fluxon or anti-fluxon. Yeah. Okay, so the ballistic flip-flop requires actually that we have a fluxon stored in the ring initially. And when we do that, we basically have we have a need to basically put in an SFQ over another port. So we've put that port's not intended to be used other than right after you cool it down for testing. And you have the input bit and the output bit that I mentioned before. They're traditionally sometimes labeled D and Q, so I kept that notation. But we're going to go into the two-polarity detector experiment before I describe the simulation of the ballistic flip-flop. Okay, so because we have those 2 polarities, we need a way to measure the 2 polarities. And we know I've already described how we measure one polarity with a SFQ to DC, and that's reliant partially on a toggle flip-flop, but we wanted to measure both. So what we did is we designed this circuit. It has a central LJJ that's sort of under test, or could be LJJs with a gate in the future. And one fluxon polarity could go to this, the other fluxon polarity could go to this port, and it's biased to basically separate fluxon bipolarity. If a fluxon comes in, because of the bias of the direction, the fluxon will want to go this way. Because of the bias direction of this, an anti-fluxon will want to go this way. It'll be forced that way, I should say. And we're only launching from the upper port in the schematic. We have a DC to SFQ, and biases will force this fluxon or anti-fluxon, if we bias it oppositely, into this LJJ. and there's no power in the middle. And you can see the photos from the design device here. Okay. So here are some results. When we intentionally launch fluxons, we can measure them. This is the regular waveform for the input to create fluxons at all the rising edges, and the output shows a switch for every other rising edge, as it's supposed to. The lower arm basically shows no signal because no fluxons are being diverted there, and the output bias, that is the power at the final detector, is 95 microamps. In the other case that we launch anti-fluxons and divert them towards the detector, it's a little different. So the launching, we have the opposite bias direction. The upper detector does not show switching, and the lower detector does show switching, but the output bias is higher at 125 microamps. And we understand that with the following problem, that basically back in the circuit, we're crossing, in the case of anti-fluxons, we're causing a fluxon to go on one side of a ground and then to the opposite side of a ground that's basically connected to this single LJJ, and that costs some energy cost that I'll describe next. There's extra energy costs for the latter case. Now, there is energy cost and it's because of the grounds. The energy cost, here's two grounds on an LJJ, and I put them on the same rail at first. And in that case, when the fluxon comes between the two grounds, we know that the flux from the fluxon in any superconducting loop will be screened. So this fluxon is applying some superconducting flux around this rail, but there's two connections to ground here. And so there must be a screening current to compensate for it. Another way to look at it is that there's a shift of 2 pi as the fluxon goes across on this long Josephson junction, and that will induce a current that includes currents between these two ground connections. So it'll cause currents to flow this way, and the currents will be split up in the middle of the LJJ section equally on the two rails. So the screening currents look like this going above and around those wires. Now, I'm going to just describe another fluxon because it's a little confusing to switch fluxon polarity, but this relates to the anti-fluxon path in the experiment, but I'm showing the same polarity fluxon. Now we have a ground on one side and the other side. When the fluxon comes in between these two, there is a screening current. It looks like it's roughly the same magnitude. It is roughly the same magnitude, and we have an equation for this. But what's worse, in this case, when this fluxon goes away from the two grounds, goes past the two grounds, the screening current disappears and the energy from that disappears. But in this case, when the fluxon goes from between the two grounds to past the two grounds, a full flux quantum is along each rail, phi naught over 2 here, plus another phi naught over 2 added, and the same on the other rail. And it's like we have a full flux quantum trapped between the ground and the LJJ, just sort of horizontally trapped. So we understand that strange addition in bias current required to operate in the continuous mode as being qualitatively related to these extra energy costs, or the total extra energy costs for transmitting a fluxon across opposite side rails, opposite rail grounds rather. Okay. Next, we have the full test circuit simulation for the ballistic flip-flop. here's another way of showing the ballistic flip-flop just in a very illustration-like way. LJJ, LJJ, the slip junction, some capacitance there, the storage loop, which stores a bit, and then a schematic here where we have more details. Now we've designed this such that we don't have the ground connection at the input because we were worried about getting asymmetric results between the fluxon and the anti-fluxon and the detector. We don't like biasing things differently. It doesn't settle well with us that we don't fully understand it. So we ended up using an inductively coupled launcher. We can't launch as many fluxons of the same polarity, but we can certainly get a fluxon to launch in here. And we do this in simulation. And here's our two-polarity detector. It still has grounds, but again, there's no grounds at the input side. There's an initialization circuit too, also inductively coupled. We just need to get one fluxon or one anti-fluxon into this storage loop to initialize it so that we can use the gate. Here's a block diagram of the same thing. Input, inductive launcher, LJJ transmission line, going to the BFF gate, which is initialized, and finally a two-polarity detector. Okay, here's a simulation of or 2 pages of simulations from the ballistic flip-flop gate. If you have a transmission line coupled to this microstrip here, and you apply a voltage with steps in time. Every time you have a voltage step, you could launch a fluxon, and we do that. There's a little bit of time delay from the input of the transmission line and the fluxon current pulse, but this shows the current pulse from launching one fluxon, a second fluxon, a third fluxon, and so forth. So we understand this launcher circuit. We use a large JJ at the beginning so that it has significant energy to switch it, and it can allow us to launch at a high speed a fluxon without using a high bandwidth for the input waveform. Finally, we're simulating a ballistic flip-flop with a periodic input of 2 positive steps and 2 negative steps for the voltage input. And we initially had an anti-fluxon in this simulation. So as you put the first fluxon in, and we had a stored anti-fluxon, remember the operations like a shift register, and a fluxon coming in will kick out an anti-fluxon. That will change the phase across that central JJ by 4 pi. And then if you put a second fluxon in, it already stored a fluxon, so there won't be much other than a little bit of oscillations here from the dynamics of passing a fluxon by the fluxon. And then when an anti-fluxon comes in, it switches the central JJ back to 0 phase difference. And another anti-fluxon after anti-fluxon will just create some small oscillations on that central JJ. And the two-polarity detector operates at the same time in our simulation. That is, initially there is the anti-fluxon detected. It goes into the lower two-polarity detector arm, and then there was 2 fluxons that came in, according to what I just told you, and that causes 2 upticks in the phase in the upper two-polarity arm, and that's followed by 2 downticks in the phase from the lower detector arm, and so forth, and so on like that. So the simulation worked. It actually included the initialization circuit too, but I didn't have time to show that. Be happy to share that with you separately if you're interested. And then there's a physical layout design that I want to show. Since the test circuit looked good, we wanted to lay it out physically. And we did it with MIT Lincoln Labs process for which included a 4 microamp per square micron JJ process, and also niobium oxide, aluminum oxide capacitor that had a large specific capacitance of around 4 femtofarad per square micron. This allowed us to shrink the dimensions of the gate relative to what we'd have without it. And you have an inductive launcher, the BFF gate and layout. I know it's zoomed out, so you can't see all the details, but it gives you an idea of what it's like. Initializing circuit, I mentioned and I showed this before. Initializing circuit looks a little similar, except we have some extra JJs there to allow extra SFQ to slip out so that we don't overpopulate this with SFQ. We just want one in the storage loop. The brancher is where the one LJJ connects to two for the two-polarity detector. And then if you zoom into that interface with the three JJs for the gate, you see a JJ at the termination of this LJJ, a JJ at the termination of this LJJ, and the capacitance, shunt capacitance across that, and finally a shunt capacitance and JJ that allows slipping of the phase at the storage loop, and as well as at input to the output. So there's the schematic, and the size of this central interface ends up being only around 28 microns on the side, which seemed acceptable to us for an experimental layout. Okay, so this is the summary of the talk. The conclusion, the ballistic logic that we've discovered uses pairs of LJJs to realize these efficient logic gates. I mentioned the efficiency can be greater than 97%. And that's reference to the energy of the bits themselves. It uses two fluxon polarities. And we talked about the two-polarity detector and operating it, and also accidentally splitting fluxons such that we stored an extra fluxon in the case of an anti-fluxon that went to this lower detector. We have a full energy analysis that will be published for that. But in principle, one can learn more by doing imaging of the flux, the trap flux. So I think that would be interesting. The discrete LJJs allowed these test structures and gates, allowed us to sort of engineer things that we could understand. And the transmission has been verified through these LJJs in two cryogenic systems, and we published the parameters of the LJJs too. Now we have a full schematic for a ballistic flip-flop, and I showed you some simulation results on that. The gate is now simulated with all sorts of circuitry, initialization circuitry, a new launcher to eliminate this flux trapping or splitting problem. And a ballistic layout has been created, and I want to mention Alex Wynn at MIT Lincoln Lab, who helped us design ground plane holes and talk with us about various SFQ issues. So that's the talk. Thank you very much.